We're going to take a look at some of the new features in the 2012 release of the Apex optical software program. In particular, we're going to look at a couple of features that will be very useful when looking at stray light analysis or doing any other types of analysis as well. What we see here is a pretty simple system. I have a grid of uniformly spaced rays as my source, and what I have here is a lens I've just brought in from one of the stock lens catalogs. And right now, a simple window. If we look at the optical properties of these components, what I've done is on the lens, I've chosen to ignore the reflected rays. What's going to happen in this instance is we will not see the Fresnel reflected rays from the optical surfaces, but the energy loss due to the Fresnel reflections will be taken into account in our calculations. And this surface here, the window, later on in the demonstration, we're going to turn this into a diffusing component, but right now it's simply a perfectly transmissive plastic window. And again, we have our grid source. So the first thing we want to do is, obviously I have this stock lens here. What we'd like to do is analyze the performance of this lens. So to do that, I might want to look at the rays in the vicinity of the focus of the lens. And there are a couple of ways of doing that. I could obviously go and figure out what the focal length is and what the focus position is, but I also can allow Apex to help me figure that out directly. And this is, again, one of the new capabilities that's been added to the software. So what I'm going to do is just go over to my Trace tab, and I'm going to trace the rays. And since I have no detector surface, the rays are just going to propagate a short distance. This length right here is part of the project settings where I ask for the rays to be drawn an additional length of 16 millimeters. But as you can see, the light is converging when it comes through the lens as expected, but where exactly is the focus? What I'm going to do is come over here into my Optics Manager, and in my results area, you'll notice that we have our ray trace listed. And if I right-click on the ray trace, I now have an option to focus the rays. What this will do is analyze the directional information about each of these rays and calculate in 3D space where the position where that ray distribution is minimized. So let me just click right on here. And what I want to do is propagate the rays directly to the focal point. So I'll accept that option and just click on OK. And now I have the data in front of me. The optimal position is at a z-coordinate of about 75.62. What I'm going to do now is simply copy that piece of information because it will be useful to me in a moment. And what we're going to do is position a detector at that location. So let me click back on the model view. So somewhere over here at that z-coordinate, we want to insert a analysis surface, a target. I have already created one, so I'll just go to Insert Components. And if I browse to my directory, I have my target right here, which is a simple absorbing surface. And let me just click on OK. Now, when I did that, the surface was positioned relative to the origin. So what I'm going to do is allow that position to float. And using the Move option, I will just move it to the desired Z position. Click Apply. And then OK. And now if we zoom back out, we see our target at its desired location. And to verify, let's do a quick trace. And as you can see, if we zoom on in here, the rays are indeed focusing in this location. These are simply arrowheads that have been drawn on the rays. Sometimes they're useful to help us see where the light is going. In this particular case, they're probably a little bit irritating. So what we're going to do is, to give you a better view of the focus, I'm going to turn off those arrowheads by going to my Project Settings tab. And on the Ray Trace display, I'll turn off the arrowheads and just look at some lines. And this is that 16 millimeter distance I was talking about after the first ray trace. That's where that number came from. Click on OK. And so now you can see that we have our light coming to a focus at this location. Bit of spherical aberration, but that's not the purpose of this demonstration, so we won't worry about that for now. And now let me zoom back out so we can see the system again. Now what I'm going to do is show you some other new capabilities that have been added to the software in terms of some of the enhancements in the area of doing stray light analysis. But in this case, I'm simply going to apply it to this system using a diffuser. So what I'd like to do is take our little window, and just on the back face, what we're going to do is turn it into a scatter surface so that the light coming from the source will travel through the lens, start to converge, but then what we're going to do is scatter that light by applying a texture or a scatter model to the surface. So let me simply, in the graphic pane, right-click and select Optical Properties, and then set Scatter Model. By selecting a surface specifically within the graphic pane, what I'm going to do is apply the property only to this one face of the component. If I had selected it within the Optics Manager, I would have applied the scatter profile to all of the surfaces that make up my window. And in this particular case, we'll only worry about a transmitted scatter. And if I click on Select, it takes me to my Scatter Manager area. And another new capability in Apex 2012 is if we open up the expanding window down here, and let me move this up a little bit so you can see them all. Previously, we've had the ability to simulate scatter using Harvey models, using what we call the random slope error, which is a form of the Harvey model appropriate for injection molded components, as well as using a simple Lambertian model. As of the 2012 release, we've added several more extensions and enhancements to the scatter modeling that will allow you to simulate texture or scatter profiles using ABG information, K-correlation data, your own mathematically defined BSDF function, as well as an M by N polynomial model. And all of these are explained in all of the online documentation that comes with Apex. But for our example, what I'm going to do is define a simple Lambertian scatterer. So let me just click on Lambertian here, and then click on New. And I already have this in my library, but that's all right. Notice the scatter model type is Lambertian, and what I'm going to call this is Lambertian 1. And then the property that we're going to associate with this is a complete total hemispherical reflectivity of 100%, so all of the light will get scattered, sort of like an ideal diffuser. And I can store this in any particular catalog. I also can add it to my list of favorites. By putting it in my favorites, then it's easier for me to find. So let me click on OK. And now I'm in my favorites area. Here is the scatter model I've just defined. And let me click on OK. Now, previously what we've been able to do is scatter relative to the specular angle or into a particular solid angle. So let's take a look at that. And what we're going to do is launch some rays from this source and then let them scatter into space. And we'll see what happens. And we'll just click on OK. And what I'm going to do is perform another ray trace. Now here's the problem. As you can see, the light is indeed scattering, but with a Lambertian scatterer, the light is going to go from each of these rays into a random distribution of all angles, and statistically, the likelihood of any of those rays scattering onto my target is very small. When I'm doing a stray light analysis, what I want to be able to do is isolate that data to show me about the energy that can possibly reach one of my regions of interest, and more importantly, give me an idea of the paths that's available to reach that surface, and the most important item is exactly how much energy of that scattered light can actually reach my surface of interest. And what we've done within the new version of Apex is provided a new geometry capability, which are what we call rectangular scatter areas or elliptical scatter areas. And what this will allow you to do is to define an area in space where Apex will preferentially scatter the rays. So in this particular case, if I'm concerned about scattered light reaching my target surface here, what I'll do is define a scatter area in the vicinity of my detector, scatter light towards that, doing another ray trace, but what Apex will do is adjust the ray distributions so that all of the light gets scattered towards my target, but it will adjust the energy in those rays to reflect the amount of energy that would enter that angular region as defined by the scatter model and the geometry of the system. So here's how it works. Let me just come right up here, and it's going to be easier for me if I reorient my view right now. And then I'll choose a rectangular scatter area. And you'll notice it's this little surface that's been added right there. And I need to do two things. First off, I need to move it into the vicinity of my target, and then I need to resize it so I'm capturing the appropriate solid angle of the detector relative to my scatter surface. So what I'm going to do is, if we remember back from our focus command previously, we want to put this again at about 75 millimeters away. So what I'll do is I will select my scatter area here, and from the Assembly tab, Move Components. And I'm not going to worry about the exact position, so let's just say 75. It's not going to really affect the angular subtents significantly, so let's just click on again, Apply, and OK. And now we can go back to our model view, and I think right now I'll save this file. And yes, let's rebuild it as well. So now what I want to do is adjust the size of my scatter surface, and my target is a 5 millimeter square. So let's adjust these sides also to be 5 millimeters. And then we can rebuild and OK. And there we are. So now we have this importance area or scatter area that isolates our detector. And what we're going to do is perform another ray trace. I'm going to have to make a couple of setting changes first. Let me go over here to all of my project settings. And in particular, what we're going to do is turn off our Monte Carlo ray tracing and allow a deterministic ray tracing. And just click on OK. So again, all of the rays that will scatter, rather than going into the full hemisphere defined by Lambertian, should all scatter towards our target surface. The other thing we need to do after changing the project settings is we actually have to modify our definition of our scatterer. So let me come over into my Optics Manager, and I'm going to select the scatter face right here, right-click and then Edit, and instead of scattering light into the full hemisphere relative to the specular light, what we're going to do is scatter towards our defined importance edge. I've selected towards edge, and you'll notice the SOLIDWORKS model page wants to know which edge. So let me just expand my tree and select the scatter area. Click on OK. And now let's run another ray trace. And we can see that indeed all of the light is now hitting our target. We can see if we look in here that the rays are certainly no longer ideally converging towards that image because of the scatter that's been applied. You'll notice it's a limited amount of scatter in terms of angle, simply because we're only looking at the angular subtents that can actually intersect that detector. So let me rotate around a little bit and highlight the detector. And the first thing I want to do is find out how much energy is on my detector. And I'll do that by looking at a summary statistics command. And you'll notice that all of my rays have reached the detector, but I'm down to about 0.1% of the total energy. So by using the importance edge, we get an understanding of how light can scatter, how stray light can affect the performance of our system. We get to trace a minimal number of rays to actually sample the surface, but we're going to get a very exact calculation as to what the total energy in that stray light is. And to prove that to you, what I'm going to do is come over here to my model, and I'm going to modify my grid source a little bit. I'll just increase my number of rays. Okay, so if I have a much larger number of rays, we should get a bit more accurate calculation. You know, we might think we didn't have enough rays to do the initial calculation. So let me click on OK. And again, we'll come over here and we'll do a trace rays command. And we see lots and lots of rays reaching our target surface now. But again, when we do analyze and summary statistics, exactly the same result. So as long as you set up your importance edge to properly sample your region of interest in your stray light analysis, you're not required to trace a very large number of rays to get the right results. And more importantly, you don't have to create significant amounts of generations of child rays to properly sample your region of interest. This will significantly enhance your ability to do stray light calculations within the APEX environment. And just to give you a full idea of what's happening, what I'm going to do is load up the smaller ray trace, and I'm going to go to the project settings. And just for a moment, I'm going to change the color of the rays just so they're a little bit more visible. So you can indeed see that the light is being scattered. So instead of having perfectly converging light, we're introducing this scatter. And if we go back to the ray trace with lots of rays, what this will allow us to do is a bit of visualization. So let me again select my target face, my surface of interest, and I'm going to go to my Analysis tab. And if I do an irradiance calculation, what I'm going to see is the distribution of energy across that surface. And I want to increase my resolution a little bit here. Click on OK. And what we see in our false color plot here is that indeed our target surface is covered, if you will, with rays. But if we look at it again in cosine space, using an intensity calculation, and we'll accept the defaults here, click on OK, what we see is that the rays incident on that surface cover a small range of angles. Direction cosine space, you can see here, is less than 0.17, and that's simply based on the area of the detector seen by the scattering surface and the area of the scattering surface seen by the detector. Another new feature in APEX 2012 that will help you do stray light analysis is the ability to determine those surfaces that can be seen directly or indirectly by your detector surface. Those are the only surfaces that you really have to worry about when you're doing stray light analysis. If the detector can't see a surface either directly or via another optical surface, then you don't have to worry about stray light from that surface actually interacting with your target face. To do that, again, it's in your Project Settings tab. Let's go to All Settings, and then Critical Surface Analysis. You can choose to identify critical surfaces, and you can either look at those surfaces that are directly seen or indirectly seen by your detector. And in this particular case, since all of our surfaces are optically active surfaces, they will all be directly seen by our detector. All optical surfaces are what we call critical surfaces. But just to show you how this feature works, let me click on Directly Seen, click on OK. And let's do one more ray trace. So let's go over to our Trace tab and just one more ray trace. And what we see here are our optically active surfaces. We understand how much energy currently is seen at each of those surfaces. And as I select the different surfaces, they become highlighted. This also gives us the ability, so rather than going up, as I did previously, into the Optics Manager to apply a scatter model to a surface of interest, we could also do the same by coming to my directly seen, or if I had them indirectly seen surfaces, select a surface, and choose to apply a scatter model, and it takes us back to our scatter model manager, just like we were on before. So again, it's simply a different way of applying the scatter model. Since we don't need to do that now, we can turn that off. So what we've looked at are some of the new capabilities within APEX 2012, in particular many that are useful in the area of stray light and scattered light analysis. We've looked at using importance areas, either elliptical or rectangular importance areas, to restrict the spread of scattered light through our systems so we can get a reasonable estimation of the scattered energy that can reach an important area. We've also looked at how to set up that type of scatter model within APEX, and we've also looked at the fact that we've added many new types of scatter model definitions within APEX as well. Additionally, we've also looked at the new focus command. Now, in our particular case, we looked at focus, but there is an additional option as well, which is to move the rays, which allows you to simply propagate the rays along their direction vectors some specified amount. So there are lots of ways that you can adjust where the rays appear to be coming from that will again help you do your stray light analysis.